So today we're going to talk ellipses, and I want to start with the definition of an ellipse. I know that you looked at how to slice the cone to form the ellipse in the video yesterday. So think about how to slice the cone, right? It goes diagonally through the cone and it goes through both sides of the cone. And so the definition of an ellipse is it's the set of points and the sum of the distances from two fixed points called foci is constant. So I'm going to show you how I can use that definition to draw an ellipse on this piece of paper. So I just have a piece of string here. The string is going to stay the same length the whole time. And I'm just going to draw a straight line here that I'm going to position my two foci on. So this is going to be a horizontal major axis. And I'm going to put my two foci just kind of a random distance apart. So there's my two foci. So those are the two fixed points. And I'm going to do my best with tape. It would be better if I had like a pin board, but I'm going to do my best with tape. I'm going to attach the end points of that string to those two focal points. All right, so there's the end points of my string. That can't move. This string is going to stay the same distance. Oh, I hope I stay on my paper. So what I'm going to do is I am going to now pull the string really tight. And as I pull the string really tight, I'm going to be forming all the points that lie on this ellipse. So can you see how, I wonder if this is far enough out for you. So as I'm pulling the string tight, it's forming all of the points that have that equal distance sum. So there's my ellipse. So we're going to talk about ellipses in a couple different ways. First of all, this looks pretty circular in shape to me. So the distance that the two foci are located affect the shape of the ellipse. They affect if it's centered horizontally or if it's positioned vertically, and they determine how kind of squished an oval an ellipse is or how circular an ellipse is. So we're going to talk about all those different pieces, and we're going to define these important pieces of an ellipse before we try to graph it. So first, the major axis is going to be this longer axis. It's always longer, and it is where the foci are located. So the major axis is always the longer axis. It might be vertical, it might be horizontal. It contains the foci. And the other thing is the total length of the major axis. So if this is the center of my ellipse, this has a length of A. So to get from the center of my ellipse out here to this, what we call a vertex, we go a distance of A. So the total length of the major axis is 2A. So 2A is its length. And I always think of the word major for longer. So it's the major axis, it is longer. So the minor axis, therefore, is the shorter axis. It might be vertical or it might be horizontal. So in this ellipse that I drew, this distance here and this distance here is B. So it has a length of 2B and minor shorter. So major longer, minor shorter. The foci are those two fixed points. And the two fixed points of an ellipse are actually located, if I go back to my drawing here, this is a distance of C away from the center. So the foci are located C units from the center of the ellipse. C units from center. And I'll just emphasize they're on the major axis. So whichever way the major axis is, that's the one that contains the foci. Think of it as the more important axis. The vertices. So how many vertices are there on an ellipse? There are a total of 4 vertices. 1, 2, 3, 4. So they are the end points of the major and minor axis, or axes, I guess I could say, plural. The center of the ellipse. So I've said the word center. The center right here is the intersection of the intersection of the major and minor axis. So the center is the intersection of the major and minor axes. And it's going to be located at the point H, K. I'm going to show you what that means down below when we talk about standard form and what H, K means. It means the same thing as it did for circles that we've worked on. I'm going to label some things in my diagram, but there is a special relationship between A, B, and C. So remember, A, B, and C, right? Those are the distances to the vertices or to the foci. So let me draw you this picture. If I stretched my string all the way over to this point, right? So I've stretched it really tight. I'm now at this vertex. How long does that string have to be? So I want you to look, the string stays the same length. So when we define this kind of string, the sum of those distances, if I want to go to the furthest point out here on the ellipse, how can that help me figure out the length of the string? Well, if you're looking carefully, this length here, right, goes from this focus to this vertex. And I have this little piece of string left. Well, guess what? If I cut my string right from here to here, that's the distance from my focus to my vertex. Couldn't I insert that little short piece of string over here from the focus to the vertex over here, completing one length across the major axis? So imagine this little piece of string I've now inserted over here. So now I go from vertex to vertex. If the string will stretch from one vertex to the other, what's the total length of the string? A plus A. So the total length of the string is constant, and the string is always equal to 2A. That's going to help us figure out the relationship between A, B, and C, because I'm stretching here, I'm stretching here, I'm stretching here, I'm stretching here. This is another important point on our circle or on our ellipse. So when I pull my string tight up to this vertex, you just told me that the string has a length of 2A. Didn't I just form an isosceles triangle, right? Isosceles just means that these two lengths have to be the same. So if this was 2A, doesn't that make this right here A and this right here A? So if this is A on a right triangle, how do I know it's a right triangle? This is a perpendicular line right here. If this is C and this is B, don't I have a Pythagorean identity relationship here? Isn't it C squared plus B squared would have to equal A squared? So it's not the Pythagorean theorem that you know, where A squared plus B squared equals C squared. But A, B, and C in an ellipse means something slightly different. It is the Pythagorean theorem. Leg squared plus leg squared equals hypotenuse squared. So the relationship between A, B, and C that you need to know is A squared equals B squared plus C squared. We're going to come back to that a lot today. So let's just, in your diagram, draw in a few key points just so we can, show what I did on my other diagram. Here's the center. Here is a vertex, a vertex, a vertex, and a vertex. And we have two foci in an ellipse. And let's just show those key distances, right? From here to here is B. From here to here is B. From here to here is C, so from the center to the focus. And then this longer distance here is A. Longer distance here is A. You might want to write down that the string is equal to 2A, just so that you remember that example of stretching the string all the way around. So lastly, on this kind of definition page, and then we're going to put it into action, I want to show you how you can write a horizontal or vertical major axis equation for an ellipse. It's very similar to a circle. So I'm always going to put my x value first. That's just my habit. X minus h squared plus y minus k squared equals 1 this time. So instead of equaling r squared, and this being a circle, an ellipse is always equal to 1 so that you can read it. So that should be inside the box. I just ran out of room. If it's horizontal in direction, like this ellipse is, the a value is going side to side. So the a squared value, the bigger value, is positioned under the x in the equation. The only difference between these two, I'm just going to still leave it as x minus h squared, y minus k squared equals 1. The only change is when you're positioned vertically in this direction, now your A is just going in the vertical direction and your B's are going in the horizontal direction. So just A squared and B squared flip-flop with each other. That's all it takes to go from a horizontal major axis to a vertical major axis. And now we're going to see that in graphing on the next page.